All right, now that you've had a little bit of time to think about question one, let's go over the answers. So part A says the set of all x, y such that x is greater than 1 and less than 2. Okay, so this is a band in the xy plane where we let x vary from 1 to 2. Y can take on any value, and we're not including these boundary lines x equals 1 and x equals 2 because of these strict inequalities. And so is the set open? Well, if you choose any point in the set, then yes, it is possible to find a disk centered at that point that will lie entirely within the region, right? You could say, oh, well, I'm a trillionth within the boundary. We'll just choose the radius of the disk to be half that distance. Then that resulting disk will lie within your region. Okay, so this is an open set. Is it connected? Well, if I choose any 2 points, A and B, in the region, is it possible to connect those 2 points with a continuous curve that lies entirely within the region? Yeah, it certainly is. I could take the straight line segment from A to B, or a more creative path like this, but there's at least one path. That's what really matters. And so this is a connected set. Is the set simply connected? Well, if I were to draw a closed curve within the region, then yes, I can contract this closed curve to a point while lying entirely within my region. Okay, and we note here that this region does not have any holes like we discussed in the last video, and so this set is simply connected. Cool. All right, how about part B? All right, the definition is essentially the same as an A, except now we have absolute values around x, and so now we're going to get two bands here. And so is this set open? And the answer there would be yes, for really the exact same reasons we gave above. Any point you choose in the set, no matter how close you are to the boundary, it's always going to be possible to find a disk centered at that point that will lie entirely in your set. So this is open. Is the set connected? Well, now we have an issue because if I choose a point, say A in this left band and a point B in this right band, then any path that I use to connect A to B will pass out of the region. Okay, so this is not connected. Is it simply connected? Well, if I were to draw a closed curve within my region, so a closed curve like say here, then yes, I can continuously deform this closed curve to a point while remaining entirely within my region. Okay, and that's true whether I choose my closed curve, say in the right band or in the left band. Right, I can do this continuous deformation to a point while lying entirely within my set. So we are still simply connected. And note here that again there are no holes in this region. Now in C we have all of R2 excluding the origin. Okay, so is this set open? Well, any point you choose in the set, is it possible to find a disk centered at that point that will lie entirely in the set? Sure, right? The only point that's excluded is the origin, right? So, if I'm within, say, a millionth of the origin, like we were discussing up here, just choose the radius to be, say, half that distance, then then the disk centered at your point will lie entirely within this set. So this is an open set. Is it connected? Well, if you choose any 2 points, say A and B, is it possible to find a continuous curve from A to B that lies entirely within your set? Yeah, sure, I could choose, say, this path right here. So it is connected. Is it simply connected? All right, so now we have issues. Okay, so if I draw, say, this circle here, centered at the origin, is it possible to continuously deform this circle to a point while remaining in our set D? And the answer there is no. Okay, so no matter what point you want to deform the circle to, right? Like you just say, okay, I want to, deform it right to this point right here. See, the problem is you're going to have to pass through the origin at some point, right? There's some portion of this circle as you continuously deform that's going to have to cross the origin, right? So for that reason, we are not simply connected. And we note here there is a hole, right? We're just punctured out the origin there, and so that hole is giving rise to this uh, non-simply connectedness. Okay, now I do want to point out here, uh, which might come as a bit of a surprise, but if you take all of R3 and exclude the origin, you might say, oh, well then is that not simply connected by the same kind of argument? Well, now that you have this extra dimension, this is actually a simply connected domain. Okay, so if I draw a closed curve like this, and you say, okay, is it possible to deform this curve to a point while remaining in D? And the answer now is yeah, I definitely can, because I have another dimension basically of that I can move around in. So I could, for example, just lift all of these points up and continuously deform up to, say, this point, and I can do that and entirely miss the origin altogether. So in other words, none of these points along my initial closed curve, as I continuously deform, will have to pass through the origin. Where again, for this example, right, the only way you're going to be able to squish this thing down, deform it down to a point, there's going to be at least one point, if not more, that are going to have to pass through the origin as you deform. Okay. All right. So lastly, we got D. Is this thing open? And the answer there is no. Notice here that the inequality is greater than or equal to, less than or equal to. So I'm including these boundary points. So if I draw any disk centered at this boundary point, no matter how small the radius is, the disk will always contain points outside of my region. So this is not open. Is it connected? So if I draw, say, this point A here, this point B here, is it possible to find a path from A to B uh, within my region? And the answer there is yeah, it is. I could just take, say this path. Okay, and that's always going to be possible for any 2 points in that region. So this is connected. Is it simply connected? And the answer there is no, again, much like what we saw in part C. If I were to draw, say, this circle around this hole, right? And then really, again, the key here is since we're working with a set in R2, we have a hole. The problem there is that I can't continuously deform this circle right here to a point. So if you choose, any point, and you say, okay, I want to deform this closed curve to, say, this point right here. Okay, fine, but again, like we saw here, there's going to be some portion of this circle that's going to have to pass through um, a region outside of our set, right? I mean, we're going to have to cross into this inner hole region here uh, somewhere, right? So we're not simply connected. All right, great. Well, that will do it. I'll see you in the next video.